Okay, welcome everybody. The recording just started. Angelo, I'll hand it over to you to introduce our speaker.
Okay, thank you, Dirk. Thank you, everybody who has joined today. So I'm very happy to introduce Matteo because he comes from my group. He was a former PhD student of mine, now collaborator. He works here, but he's also has been working in Belfast with Mauro Paternostro. He's still collaborating with him there. Now he has his own independent career about collapse models, which is the topic of today's talks, and about the phenomenological possibility to test them experimentally. So do some phenomenology about these models and compare them with experimental data. And by now he knows more than me about that. And together with other activities in quantum information, quantum thermodynamics, open quantum systems. That's his background, more or less. And today's talk is about testing collapse models in the lab and space. I go by memory, more or less.
Yes, exactly.
Okay, so Matteo, please go ahead.
Thank you very much for the invitation and for the introduction. So I will share my screen first of all. Can you see this? Just yeah, fantastic. Okay, so as Angelo was saying, the title of this talk is testing collapse models in lab and space. So for whom is not familiar about the argument here, the context, I will give just a brief introduction into the topic, giving some flavor about what are collapse models, and then trying to also understand which is the state of art of actually testing these models, and which are for possible future perspectives in such a testing. Okay. So the idea is a little bit related to which are the limits of quantum mechanics, or more precisely of the quantum superposition principle. So what we know is that there are obviously some microscopic and macroscopic systems, and we usually divide them as being part of the quantum or a classical world. In the quantum side, we have a really nice superposition. On the classical side, we instead have really well localized systems. And so, for example, we have non-delocalized, not placed in a superposition dog or cat, if one prefers. So standard quantum mechanics, in a way, divides these two worlds. But the Copenhagen interpretation, to be a little bit more precise, assumes a division between the two, which is not really well marked. And so it's not really clear which are the observers and which are the systems being actually observed. And so this is a mysterious somehow. So Weinberg, using Weinberg words, it's a mysterious division between these two realms. What we would like to have instead, starting from the idea that quantum mechanics should be some universal theory, so covering all the length, so from the micro to the macro scale, is to have some unified dynamics, unified theory that covers everything. But then again, also here using Bell's word, no? So which are the properties? What characterizes a system to be the measurer and not the system being measured? So again, we have a little bit of problems in putting together things. An option that usually is called as a solution is to say, okay, the environment, the coherence that one has in typical experiments is actually the process that makes system localized, and so makes the classical system being classical, and the quantum one quantum, in the sense that for quantum systems you can still have this superposition, while for the classical one you cannot. But again, where to set the bound between what is the system, what is the environment, also because also the environment is made of quantum particles, then this again is a little bit arbitrary. And so again, this is really similar to the Copenhagen interpretation problem. There are possible solutions, just here to name a few, and I will focus here in this talk on the last option, which is the one given by collapse models. collapse models are essentially a modified quantum theory, and the modification that one brings into the Schrödinger equation are related to a stochastic noise and a nonlinear dynamics of the wave function. And they are tamed in a way that you don't have really any effect at the microscopic level, but through some amplification mechanisms, which is built in these collapse models modifications, instead you have a really strong effect at the macroscopic scale. And so in this way, you have some natural transition between the microscopic and the macroscopic dynamics, so the quantum and the classical transition in a way. So how to modify? So here I was talking about stochastic and nonlinear modifications, but this does not come from, say, just an axiom, but is constructed in this specific way. So one can think, for example, of modifying quantum mechanics in different ways, which are not the stochastic nonlinear. So, for example, one case is to say, okay, let's modify the dynamics just linearly. So I take my Schrödinger equation, which is essentially this is H, this is the Hamiltonian of our system, and I add with an I in front another self-adjoint operator, and this is calls a little bit for an evolution, which is some decay in probability. This is typical, say, for example, in scattering theory or in particle physics, where you want to some particles to just vanish, no, and so you add a term like this one. But then, if you compute the norm out of this, so the evolution of the norm of this state, you find out that this is not conserved. And so you have to account for this state. So essentially what you do is to normalize by hand your state, and then you take this function, this wave function, normalized wave function, you put it back in, and what you find is a dynamics which is actually nonlinear in the wave function itself. And so also if we want to modify, say, with a minimal invasive modification to the Schrödinger equation, what ends up is that we will end up with a nonlinear term in any case. Okay, so let's say that instead we want to modify the dynamics with a linear modification, which is steady stochastic. And this is what more or less the coherence models do. So you have an Hamiltonian plus an extra term, which is stochastic. So in this case here, the dynamics is actually is not conserved, so we are happy about the conservation of the norm. However, what happens is that eventually this effect here is just a phase in our wave function, a stochastic phase in our wave function. So this is the case, for example, with H just set to be equal to 0. What happens here is that when we compute the probabilities, in particular the populations, so the probabilities are, so the populations of our set, what happens is that these are preserved in time, meaning that if we construct as initial state of our system, delocalize a system placed in a superposition plus A minus A, then the populations, which actually are the probabilities of finding the particle in A, these do not change in time. So meaning that our state, maybe it's, so the interference contrast between the two parts of the superposition is actually killed, but the state just remains delocalized. And so this means that it does not allow for an actual collapse of the wave function in A or minus A, which is said what we would like to have in a collapse model scenario. Okay, so then another option is to consider some deterministic, so non-stochastic, non-linear dynamics. But we saw that the linearity is necessary for the norm conservation at the level of psi. But if the dynamics is deterministic, then also the level of the statistical operator, the dynamics will be nonlinear. And this allows for faster than light signaling, which is something that we don't want for a good theory. So essentially, to summarize a little bit, we want both these features. The dynamics should be both stochastic and nonlinear. And so the strength between these two processes, so the stochasticity and the nonlinearity in the dynamics, allows the state to remain normalized and to avoid faster than light signaling. So these are the two parts. Okay, to introduce a little bit the idea of collapse models, I would like to start with the Ghirardi-Ribini-Weber model. So this is the so-called GRW model, which is the simplest one, but already gives a really the feeling of what's happening. So the idea is that we have a stochastic localization of our wave function with a mean rate lambda. And this localization occurs in space following this process here. So we have the wave function. This is multiplied by an operator L, which localizes the particle in position. This is the Q around a position, specific particular position A. So this is the operator Q, and this is A is the particular position we want to localize it. And then obviously we have to normalize this state. The probabilities of localization around a specific point A are just given by the modulus square of the operator L applied on psi. And between two consecutive localization, one just have the free Schrödinger equation. And so the idea is this: we have Schrödinger equation, we have a localization, and then the Schrödinger equation again. So this process is then described in terms of two parameters. One is lambda, which is the collapse rate of this process. So essentially this rate here of localization, and the other one is RC, which characterizes which is the dimension, the action of this L operator here, which is just a Gaussian if you want. Okay, so the effect is the following one. Consider a superposition, which is in a superposition of being in A and minus A. Then we apply our collapse operator L, and then what happens is that one part of the superposition is killed, while the other one is enhanced. So this is actually the effect if L is again centered in the same A. If it's centered not actually in the A, but somewhere in the middle, then this with the wave function will be just a little bit modified. If it's centered in say in 0, for example, then the wave function stays there. But this is a stochastic process happening in the whole space. And so essentially what happens is that here you will not have any effect, but eventually when you will have a collapse instead in A, you will have an effect like this. Then we have the amplification mechanism. So consider that instead of having one particle in a superposition, we have two particles. And these are the two wave function of this particle. But still,
Matteo, I interrupted.
Yes.
There is a question for you. What is the subscript C?
This subscript C here,
Yes.
I suppose. This is just the name of these quantities. This is the correlation length, say, of this of this process. Eventually, I hope this answered the question. Okay, so we have the two particles. They are, say, linked together, and now we have still our process, collapse process L, which is described by L. And what happens is that they will collapse, but they will collapse with a rate which is twice as that of the single particle, because the two systems are together. Okay, so now this was the GRW model, and I hope it gives the flavor what's happening in these collapse models. But we can say go a little bit further and consider a general structure for a stochastic equation, this stochastic and nonlinear equation describing the collapse dynamics. So this is the equation. Again, we can see the first term. This is just the quantum mechanical Hamiltonian. So this is the Schrödinger equation essentially, and then all the rest are collapse terms. We have a measured operator. So this was the L operator in the GRW, so to say. And there are different options for this operator here. For example, mass density, position, or or something else. We have the nonlinearity kicking in. So you see, is the M operator minus its expectation value, where the expectation value is computed on the same state that we are considering. And then this white noise, or I'll say a stochastic process, can be white, can be colored. Let's, for the sake of simplicity, assume for now that this is white. And then the last term, it comprises a noise spatial correlation, D, and is described essentially which is the characteristic length of this noise W. And the last term here essentially is needed, is the Ito term, and is needed just to have a well-normalized wave function in time. There are two main models in literature that one wants to study. One is the CSL, so the continuous spontaneous localization model. And this is a fully phenomenological model. We are just saying, okay, our noise spatial correlation is a Gaussian. The measured operator is the mass density. And we still have these two constants, which one is the collapse rate lambda, and RC, which is the correlation length. And so, again, the same C appearing here. The second one instead is the Diauchy-Penrose model. This is related to gravity. Essentially, the idea is that if an object placed in a superposition has enough mass, then will deform the space-time, but the space-time, so gravity doesn't like it, and so we'll just move it and let it collapse. And so the correlation, the spatial correlation of this noise is related to gravity, so G1/R. And just because this correlator here has the usual divergences for a small length, then one regularizes, say, for example, mass densities with some Gaussian, just to smooth out these standard divergences. And so one has a free parameter of the theory, which is R0. Okay, so now, so this was in a way the theory side. Let's see a little bit more on the experiment, because eventually, and this is, I would say, really the step forward that the theory, that the field had in the last just less than 10 years. So there are two family of experiments that are relevant. The first one is the most straightforward, the most natural one. We have a system, we just place it in a superposition, and then we see if this superposition somehow is skilled. So essentially, interferometric experiments, which is what this interferometric works exactly in this way, are relevant, and one looks, for example, at the contrast of these interference fringes in the experiment. There is also a second class of experiment, which is that is the one of non-interferometric experiments, which accounts for all experiments that are non-interferometric, meaning all experiments where the system that you want to use to test is not placed in a superposition. It exploits a broader family of effects, but in a way or the other, they are related to the fact that in the dynamics, you are including some stochasticity. And the stochasticity actually is just a noise. And so the action of this noise on the system will make the system jiggle in a stochastic way. And so one just looks for these extra jiggles in your system. Okay, I will take the CSL as a little bit of a figure of merit for collapse models, mainly because it's the easiest to be studied, but also because it has it's fully phenomenological, so one is not really considering something specific here, but still leaves open doors for more specific models here. So this is the parameter space. We have lambda, we have RC. There are two sets of theoretical values for these lambda and RC parameters. One is the one of GRW, which was proposed by the GRW article, GRW model. and one instead is related to was proposed by Adler. So the idea here is that the collapse should be effective at certain timescales and length. So the length is somehow easy because so this is 10 to minus 7, 10 to minus 6 meters, which is more or less the scale where one goes from really microscopic to really macroscopic systems. So this is the mesoscopic regime in a way. For what retains instead the time scale is a little bit more complicated because it really depends on which is the system that one wants to make collapse. So for example, the GRW idea is that below this region, and this is also the idea of this theoretical bound here, essentially, if lambda is smaller than this, is weaker, so if the collapse process is weaker than this value here, then essentially one would have mesoscopic or macroscopic superposition, and this is not what we observe. So essentially, this is the reason why every value below this line here essentially is excluded. Adler's idea is instead considers a different process, which is the late imaging of process of an image, say when I do a photograph. So how much time do I take to form that image on a film? And so in a way, this is the process that Adler considered, and these are the values that he gave for it. Okay, so interferometric test. I have a single slide for this interferometric test because I think that in a way there are quite natural tests, and so one already have the feeling of what is happening here. One takes a system, place it in an interferometer, so construct this superposition, waits for some time. During this time, the collapse will take place or not, and then reconstruct the superposition. So puts the two parts of the superposition again together, and so really sees and can quantify which are the interference contrasts and which are the possible reduction due to collapse models, but also environment. And so what happens here essentially is that one can only pose some upper bounds on this parameter. In particular, at fixed value of RC, one is posing an upper bound on the value of lambda. So essentially, the lines here are taken as there is no environment acting on your system, but there is just the collapse mechanism acting on the system. So this is the maximum value that collapses can, so that lambda can take, so the maximum effect that collapses can take. And there are four different experiments here that consider different system placed in a superposition. So these blue and red arrows here are both related to the superposition of macromolecules, just developed on different experiments, and you can see here there's a big gap also in the years of this experiment. The reason was that for achieving some dimension of these macromolecules, so these are 10 to, if I remember correctly, 10 to 6 AMU, so atomic mass units. So they had really to develop an ad hoc strategy to place this particle in a superposition. So pushing, so taking particles larger than this in this Kapitsa-Dirac-Talbot-Lau experiments is really hard. So one would have to reconstruct from scratch essentially the experiment. So it's not just an incremental improvement, but it's actually a fully complete different experiment. This experiment here was really nice and gives you also an idea of how this process works. No, so this is an atom interferometer experiment. They were shooting atoms vertically, and while doing this, creating a superposition. And the time. What is important here is the time scale and the time and the patient length of this superposition, which are respectively around the second and the half meter. So this is a huge in time and huge in space superposition, but eventually doesn't really pose really strong bounds in this parameter space, because the fact is that the masses that are involved here are super tiny, are single atoms experiment essentially. And so one instead would like, so these are really in the microscopic regime, the microscopic world. Well, so superposition there are expected. What we would like to have instead is to have or not have superpositions with massive objects. On the other hand, say, this is an experiment that was made with diamonds, with two diamonds that were placed in entangled together. And one was looking for how disentanglement essentially is decaying in time. In this case, the time scale is really short. The movement, so the superposition of this, so say, single diamond left plus right, so this distance left plus right is really tiny, but the mass of the diamonds are huge. But again, because of the small time scales, because of the small superposition distance, then one is getting a weak bound in a way. Okay, so this is the figure of merit for the interferometric tests. And this one instead is the same figure, same dimension, but for the non-interferometric test. And as you can see already from this image here, we have a lot of different colors, a lot of different bounds. And I will try to go through not all of them, but at least families of color. I will put together families of colors here. Okay, so the first one is the one from cold atoms, which is this red region. And here the idea was to trap a cloud of cold atoms, let it freely evolve, and then trap it again. And trap it again in a particular way, so that essentially what happens is that the temperature of the initial cloud, which was at 1600 picokelvin, is instead lowered down to 50 picokelvin. This is the so-called delta kick procedure. And this works because essentially the particles will expand at a velocity, which is, so the further one single atom goes, the higher was the energy of that particle. And then what one does with switching on this potential is to kick back that particle with an energy, with a force, which is proportional to the distance that travel back. And so essentially every particle, so the faster particle are kicking back with a stronger kick. The slowest particle are essentially remain untouched. And this way one can really push down the temperature of the entire cloud. Okay, so what happens here essentially is that so one has a measure of the initial temperature, of the final temperature, so of the energy, and one can account which is the action of the collapse mechanism during this protocol. And eventually, what collapse models say is that the energy of this system here should be higher, and depends on the value of lambda, how much higher. Here we have an error for the temperature, and so this can be used to bound the value of lambda, and this corresponds to this red region here. I go to these two green lines here, to these green regions. This is a nanomechanical cantilever experiment. So we have this trampoline, this cantilever, on which is attached a small sphere. And what one does is to look how the sphere jiggles because of different noises. For example, thermal, seismic, and collapse noise as well, no? And so if one assumes that all the noises are actually due to collapse models, then one is able to put a bound corresponding to this vibration. And these are, depending on the dimension of your system, are these light green and medium green bounds. Then we go to the blue regions, the 3 blue regions, but the idea is really similar. So these are gravitational wave detectors, LIGO, Auriga, and LISA Pathfinder. So these first 2 are actually gravitational wave detectors. The last one is the Pathfinder experiment, so the prototype for LISA, which will be a gravitational wave detector in space. But eventually, the idea is the same as before. We have a mass. These are big masses, so 40 kilograms for LIGO, tons for Auriga, 2 kilograms for LISA Pathfinder, that are hit by this collapse noise. And so they jiggle, essentially. And depending on how much they jiggle, then one is able to put different bounds on the dimension, or on this parameter space. What is interesting here is the following. We have, so this, you're starting to see this V-shaped bounds, and the position when these V's are centered essentially is the characteristic length of the mass that you are considering. No, so for example, for LISA Pathfinder, this is around 5 centimeters. For Auriga, this is 2 meters, if I remember correctly. Instead, for LIGO, this is of the order of kilometers between one mirror and the other mirror that are here. And so this is here. So, but the single mass is short, is 40 centimeters. Okay, so but the idea, you can see it here, no? So the bigger is the object, the more on the right of this exclusion plot I will put my V. Okay, then we have instead levitated particles, levitated nanometric oscillators. So this is a pole trap, which is essentially we have our silica particle, which is sustained, is levitated by using electromagnetic forces, and it is just detected optically, for example, or a magnetic trap, where a particle is just sitting in a magnetic trap developed by some magnets around. In this case, we have these two bands here, and the reason why these are this quite high in our perimeter space is that these experiments were performed at room temperature, while, for example, these green experiments here were performed at 1 Kelvin or millikelvin temperature. So there is a jump, say, in also due to the temperature of the environment that you have around your system, and obviously this environment is also kicking your system. One can exploit also different things, and so this plays a little bit in how to think about possible modifications. So also from the theoretical side, how should I modify or possibly modify an experiment so to enhance these effects, you know? And the idea here was to add to the cantilever that we saw before. Is the same cantilever actually, not just having the mass, this spherical mass here, but an extra multi-layered mass, where the distance between the thickness of this layer here, which are made of 2 different materials, can be choose more or less freely, and we choose that dimension be more or less 10 to minus 7, which is the value of RC that one is interesting eventually in testing. What happens is that the effect on so the amplification of our problem, of our collapse mechanism, hits exactly the values, so it's enhanced at the values of 10 to minus 7, exactly as we had this coherent action, and so this V-shaped bound centered in the dimension of your system. Now we have an extra V, so we have a W eventually, where this second V here is centered at the dimension of the thickness of these layers. And so one can think of, okay, what happens? So if I have these layers to be more thick, then this V will move to the right. If these are less thick, then we'll move to the left. But this is more or less the idea here. Then one can go also to different family of experiments, and these are related, say, from really some fundamental physics idea. No? So if you have a charged particle and this is accelerated, what happens is that also classical will just emit radiation. No? And so one is exploiting this idea. I have the particle. This particle is hit by the noise, by the collapsed noise. Then after some time, will emit radiation. So if I'm able to say consider some specific material, and I'm able to well characterize the emission of that material in some specific range of energies, for example. So, for example, in this case, what was considered was the germanium sample, and the range was that of the X-ray emission. Then, if I see some extra emissions which are not described by the standard model, then that could be a signature of collapses. Turning this argument upside down, if I don't see any emission, then this means that the value of lambda, so this collapse rate, should be small enough to not having this emission, and this translates essentially in this orange bound. With a really similar idea, one can think, okay, what happens then if I have a thermometer somehow, no? So if I have a thermometer and I know that the temperature of the environment around the thermometer is really well known, then if I have a collapse mechanism that acts on my system, will raise the temperature of this system. And so essentially, you can think of this big. This is the core experiment, but essentially this is a big thermometer, which is used to detect. This is double beta decays, but the idea essentially is the same. If I have a decay or if I have a collapse, then the temperature, what is measured by this thermometer, will be higher than what is expected. And so essentially this, or again, turning the argument around, I don't see any increase in the temperature, and so this means that this is the bounds and this is was the yellow one. And in a similar fashion, one can consider also not just say thermometers which are in the labs, but also natural thermometers in a way. So, for example, this was the idea of using astronomical systems, for example, Neptune, and these systems give us an indication which is the temperature of their temperature, and this is done via the black body radiation. So we know which is the temperature, and then we can say, okay, let's assume that this system here is just an equilibrium situation. So it means that the entire temperature, the entire energy that is emitting via black body radiation needs to come from somewhere. And this can one of the processes. Then, so again, it's a really conservative approach. Let's say all this energy comes from CSL or collapse molecules in general, no? And so you just equate these to in and out energies, in and out flows of energies, and essentially you get you get the bound, and this bound is this brown bound here. Okay, so essentially this is the summary a little bit of these ideas, and you can see the family is much wider. The family of experiments that one can exploit, or ideas that one can exploit, is much wider in the non-interferometric family rather than in the interferometric family. Okay, so really fast, one can do really similar things for the Dioschi-Penrose. The Dioschi-Penrose model is a little bit more tricky because of the 1/r. And so a lot of this experiment doesn't actually pose any interesting bound on the values. Instead of having an upper bound on lambda, we have a lower bound on the values of R0. So essentially, these values here, so from the left, right, are those excluded. And people employ the experiments of Lisa Pathfinder, this Neptune idea, and the X-ray emission to exclude parts of this parameter space, one-dimensional parameter space. What is interesting is that essentially the first idea of Penrose, which was proposing that the dimension of this R0 somehow is related to the dimension of the wave function of the system that you are considering, essentially is excluded. And so it already, one sees some cracks in the model. But okay, to fully, so because this is this R0 is a free parameter, then one should exclude really the full R, or from below or from above, with some other argument. Okay, what about future experiments? So an idea could be, let's move experiments to space. Why is that? So the main problem for the interferometric experiments, and this is why these interferometric experiments somehow also are hitting some barriers in their development, is that you have a really limited free fall time. This is because we just have Earth, and eventually particles that are shot also vertically or horizontally, they will just eventually hit ground. And so you would like to have much longer, say, free fall times to perform the experiment, but this means that or you're going really to some skyscrapers, or you should think something different. And eventually, this gives, so this is the idea, is that you have a Talbot time, which describes which is the time that you need to actually be able to construct this superposition and put it back together. And this is related to the mass of your system. So, and you see, bigger is the mass, longer should be this time scale. And eventually, this is the record, and it's related to the mass of your system. But if you want to go up in terms of mass, then eventually you are hitting some point where you have to move experiments in space. On the other hand, also for the non-interferometric experiments, having long free fall times is important, because if you have a system that is attached to a cantilever, then the noises that are acting on the cantilever will propagate on your system. But instead, if the system is just freely falling, then there is not such a propagation of noises. And so you are really just looking at the noises acting on the system itself. And you can also see there is not just this effect that's important. What is important also that you have an enhancement in the collapse. So for example, this is the comparison between the time scaling of the collapse effect in the free particle case, so free falling, compared to the one in an harmonic oscillator. So essentially, it's trapped, or it's attached to a cantilever or something similar. And you can see that this guy here grows linearly, while this goes to the time at the third power. So the effect becomes much stronger, meaning that you have this enhanced way to measure this effect, this collapse noises. Okay, which are the almost space possibilities? One is the Bremen drop tower. I will, for the sake of time, I'll jump a little bit more faster here. We have few seconds, 4.6 seconds free fall time if we just let the system drop. But if instead we shoot it up and then let it drop back again, we essentially double this time. The problem here is that this experiment is really limited to 3 runs a day for a couple of days. They are not giving you more than this. And so essentially the statistics that you have, it's around 20 experiments, and from 20 experiments we know we cannot really get much out of it. On the other hand, we will have the Einstein elevator. This also gives 4 seconds of free fall time, but a much larger number of runs per day, and this will be really a big step in that direction. The second step towards space is given by sounding rockets. So these are rockets that are sent to almost space. There's in total some 15 minutes of free fall that you can exploit. So they are shoot up, then you start your experiment. Here already you don't have any forces, it's not gravity. And so the experiment within it's free falling with respect to your capsule, and then until you are essentially to the ground, you can make the experiment. And 15 minutes doesn't seem much, but in terms of these experiments, also 10 seconds, 15 seconds are actually a really long time. And so what you can do is to do a sequence of different experiments for the single shot of this sounding rocket. But eventually also the cost of this is not that you can shoot a sounding rocket every day. No? So there is a lot of preparation between, and the cost is also quite high. On the other hand, one can really go to space. No? So for example, one can consider experiments sitting on the International Space Station. So this is one of the first probably quantum experiments in space. It's CAL, the Cold Atom Lab, which is just sitting in this box here. In this case, was just an experiment on BECs. So to create BECs and with 2 different species, and possibly next step will be to make interferometers, interferometer experiments with this. And the free fall time here is virtually infinite. It's virtually infinite because what happens is that the space station is actually falling to the ground. So after a few days, they have to boost the satellite up, and this is free falling just because of the atmospheric drag hitting on your satellite. The ISS is not really the best place where to run an experiment because of different technical situations, technical things. So one is that there is no super specialized personnel on board, not for quantum experiments. So essentially what you have to deliver here is just a box, which is how everything in it, and will run independently on what's actually happening. And the second motivation is that there are people. And so eventually people means noises. But noises due to not just people just literally jumping around, but also noises because you want air, and that air needs pumps, and so you have this kind of vibrations that are in the satellite, and it's really hard to isolate this kind of vibration on a satellite. And so the idea is, what if we develop an ad hoc experiment on a satellite? So this is LISA Pathfinder actually, but some sort of LISA Pathfinder experiment where you do just an experiment for testing quantum mechanics or collapse models, no? And here this is an idea. This was proposed. The path towards space is definitely not easy, also in terms of bureaucracy. But if this works, and this gives actually the prediction that we computed, then the predicted bounds can go really, really down, and so cover really almost the full perimeter space that was not covered by other experiments. And so this is really interesting, and one would like to push more on this. There are also other experiments. So the STARQuest mission, for example, is to perform interferometric experiment using cold atoms again. And one can think of different experiments, for example, interferometric experiments or non-interferometric ones. But here now we have really this long free fall time. So, for example, 50 seconds free fall time, and this would already allow, under some hypothesis, obviously, to hit this GRW value here. And I think this is the last slide. There are other opportunities. So this is the NYX opportunity. So recently, ESA gave this opportunity to run for an experiment. So propose, apply for these grants, but more than grants, space on a satellite. So there's this payload mix where one is able to perform their own experiments inside. And so essentially they are putting the payload and the time and the shooter, so this will fly. You are just putting the experiment in it. And Christian Vogt and Henrik Ulbricht from Bremen and Southampton won this call, and they will run 4 different parallel experiments, optomechanical experiments, which mainly will be proof of principle experiments of quantum mechanics experiments in space for testing quantum mechanics and gravity, possibly. The big problem here actually was the timeline, because essentially in less than 1 year and a half, they had to start the call opened, and then there is after 1 year and a half, there is the launch of this experiment in space. So the timeline is really tight, and then we will see what these guys will be able to deliver for that time. So stay tuned in a way. Okay, and so this is the summary in a way. I put a couple of images just to I like this summary with figures. Yeah, and if you have any questions, I'll be happy to answer.
Okay, so thank you, Matteo. For the talk, I already see a virtual applause we have. Are there questions also?
Yes, Angelo.
Go ahead.
Okay, yeah, thanks for the very nice talk and overview over all these different opportunities to test the parameter space. A little bit blasphemic question. So suppose the bounds that you have shown, I think 3 or 4 slides ago, that even somehow negate the GRW value. Yeah, for example, this
Yes.
50 seconds free fall, and I think 1 slide before you had even somehow proposals for even tighter bounds. So where will the story go if these bounds are so tight? I mean, of course, there's still some space left to add some new dots somehow where the parameters can go. But suppose in some future, I mean, all these things can be excluded. What are the degrees of freedom in these CSL models? For example, colored noise, for example, other things.
Perfect.
Where the story would go.
Thank you for. Then let me answer with this slide here. Yeah. So the first one is definitely so one can play a little bit around with this equation and see, as you said, which are the degrees of freedom one can play with. The first one that comes to my mind is actually the question why we would like to impose a white noise. This is not something physical. It's not something that you have in nature. Usually, all the noises have some frequency dependence, no? And actually, this is the case. If one changes this spectrum of this noise, so making colored, meaning that after some frequency, for example, you have a cutoff in this spectrum, then essentially what happens is that all the high frequency experiments they lose this strength. But on the other hand, you have that, for example, interferometric experiments, they don't lose strength. And also long time experiments, they will not lose strength. So, and this is why these space experiments here are really interesting. No? We have really long times. So this is not important. We are just keeping all the noise that is kicking our system. And so will not be a big difference. And in this particular case, for example, this is, again, these are interferometric experiments. So they are really robust towards this modification. Another option, okay, I could jump back to the same equation, but essentially it doesn't really give you much of information. But the idea is here, is the following one. So collapse models, what they do is to heat up your system. So increase the energy of your system. And eventually they do it with some finite rate. And so this is okay. But eventually, asymptotically, the energy of the system will just blow up. No? The rate is really, really tiny, but eventually it's not something that you would like to have neither in a phenomenological model, no? And so you want to play a little bit with, so modify a little bit the equations and eventually make it, for example, dissipative. What happens with dissipative in this dissipative context is that, again, some experiments remain robust, some don't. And so again, this figure, so this image here, this parameter space is modified somehow. But again, interferometric experiments don't move too much. So again, one would like, well, obviously depends on a lot of different parameters, obviously, you know. So I'm not fully 100% sure that, for example, for macro, for this experiment here, there are no modifications. But for example, for the experiments that I was showing here, they are robust if one introduces, for example, dissipation. Does this cover your question?
So yeah, thank you very much. But maybe if I could put the question a bit more extreme.
Yes,
like,
please.
Is it thinkable? But I really do this on purpose now. And it could be a stupid question, but is there some analysis or is there some knowledge about, like, in which range, for example, there wouldn't be degrees of freedom left in the CSL models to then still say, yeah, okay, this bound is broken, but now we can tune this and that or adjust the degree of freedom. So is there any bounds known of how tinkering with the CLL equation wouldn't allow to adjust in a sensible range? Or is there always a little bit of freedom somehow to play with? Yeah.
You know, at the level of testing it, because eventually you want to test these kind of models, there is some path in trying to understand which are really the features that you want still to keep, you know, in your equation. So you can modify everything, but those features is something you want to keep. And those features are essentially the ones why you constructed this kind of models, no? They are summarized here in a way. You don't want any action or really small action at the macroscopic level, but strong action at the macroscopic level. And so essentially you want some collapse somehow, somewhere. There are arguments why you would like to have, say, a mass proportional term, which is this amplification mechanism. Why have it in position? Because you are measuring things in position, and so you are not seeing superposition in position. So this makes sense also.
Yeah,
so I will retain these features here, no? But eventually,
I think that they don't make sense. Yeah, my question was more, I mean, you somehow have this operator M. I mean, certainly the Hamiltonian we grant now that it's probably the right.
Jump here, yes.
Then we have this operator M hat that you have. We have the W.
Yes.
And
the W and the D and the form of this correlation, no?
Okay, and the question was really mathematically, I mean, how much freedom is in these parameters to cover somehow experiments? But it's probably very hard to know.
I can answer, it's infinite. D is a function, it can be any function, it can have infinite parameters. So if your question is mathematical, there are possible parameters. Of course, we are doing physics here, so there is a criterion of reasonableness.
Yeah, so
beyond which
question
you
was,
say
I mean,
you give up.
I understand, yeah, but my question was rather like in which of the reasonable regimes would you be pushed so much in the corner that there's nothing to tinker with anymore? Yeah, is that in reach, or is it thinkable, or at the moment is it still?
I agree with Angelo. The choices here are really
Well, let me be ironic there. If you give me a mathematical definition of reasonableness, I can answer your question.
Yeah, but as you're a physicist, I thought people thought about this.
But maybe to turn it around to Dirk, suppose if you have whatever data, could you always find a collapse model such that you're still fine?
Mathematically speaking, yes. Mathematically speaking.
Okay.
The point is that, let's say you have a noise. This noise is a correlator. It's unlikely that it is white. Probably it can have a quite complicated correlation function, but more or less it has a rough cutoff. So I would say that there is one parameter. There is. What is the value of this cutoff? No one knows. So if you, it will be experimentally extremely hard to push it down to zero. Very, very hard. So if you push it down to zero, you exclude the model. But it will be vastly hard to do that.
So, but maybe a last very short question, and then I shut up. Could it also be thinkable this is WT is dependent on the system that you're probing, or do you think of the
well, the
WT
dependence somehow is in M, no? So you can see, just think this as being, say, the mass density. So you are measuring where is the mass, and then you're just multiplying by W.
Yeah, I was thinking about the coloring of the noise, for example.
No, but Dirk is always a mean mathematician. So W of T is independent of the system. You know, if you make it dependent on the system, you might not have a linear dynamics anymore, which would allow for superluminous signaling, likely. But there is a reason why the noise is like that.
Okay.
Well,
so one boundary for tinkering.
I would say, for example, if you could have different W's for different kind of particles, for example, no? So say you have bosons and fermions, they might have different B's. You still have a good equation.
Okay. Yeah, thank you very much. Yeah.
Okay, thank you. So the next one was Lev. Nice to see you again after a long time. Please.
Thank you for the talk. First, may I make a small correction to your slide on GRW?
Go ahead.
Labs, whereas you have a pictures with Gaussians.
Yes. This one.
Yes.
Which one? This one.
You see, if I understand correctly, let me. This is a picture after a collapse somewhere here, correct? This is what you believe.
I have the system being two particles in this case.
First, it was equal Gaussians, and then the collapse was here, and then it's collapsed to. Show now the collapsed way. The next one, yeah.
No, this one is the collapsed one.
Yes. So, and I believe that the collapsed one is really something like this. I cannot really draw, but this one is not symmetric in any way because it's an optical illusion that when you multiply it by Gaussian, you multiply by a straight line. Really, it's not a straight line. It's very high inclined line. So it will be very much distorted toward this part. It will be much less here and much
Sure. But this is not
very important for the question of tails, because the tail world will not be like our world. It will be, everyone will die there very soon.
I agree. This was just a graphical way to explain which was the philosophy.
You had to draw the correct, I think.
Okay, I will modify this.
But now this helps me to ask a conceptual, motivational question. You started with a nice introduction and said, if I'll do this, it will not will be proper in this way. It will do this. It will not be proper in another way. And then you said that, oh, what we want no signaling. No breaking of signaling.
Yes.
Relativistic superluminal signaling. But I think that what I kind of, my impression from relativity, that I don't want any superluminal action. And all these collapse models do have superluminal actions. They do not allow signaling. But if you start with, again, with this experiment with the two bumps, if you don't do anything and wait, you will have these two symmetric bumps. But if you decide to look on one place, then the other side, the bump will change. It will grow up or will roughly disappear or will be very small. So although this does not allow signaling because the probability for each one is half, so you cannot signal with it. But you can change something far away in superluminal manner, which makes collapse theory, I think, not attractive because they break the spirit of special relativity. Well, what is your take on this?
Okay. I will try to answer because I definitely am not an expert, as Angelo is, on these technical details. Let's take another example, not collapse models, but just standard quantum mechanics. And then you have a particle which is localized in a position. It's a free particle, it's a free Hamiltonian. And so I just switch my interaction. So I leave my particle evolving. And what happens is that after an epsilon in time, you compute the probability of that particle being in plus infinity. What happens is that probability is not mathematically speaking zero. It's something you can.
No, but again, you use non-relativistic quantum mechanics, which of course, it's,
yes, and
no one will say it's correct. So if you lose,
what I'm doing here, what I'm doing here is just to use non-relativistic collapse.
But it's definitely wrong. So why to test something which we know it's wrong?
But I would have to interject here. I mean, we all know about Bell's inequalities, and Bell's inequalities is not about quantum mechanics per se, it's about nature. And we know that nature has these effects, and I would put it the other way around, Lev. Every theory that doesn't have these effects doesn't account for our nature. So I don't see where your criticism lies.
No.
I mean, no signal.
The Bell inequality by itself, what causes action at a distance is collapse. And if we remove collapse from quantum mechanics, of course we have to pay for many words, then I cannot change anything far away. And the collapse does it explicitly. And then we can use Bell inequalities. We cannot use Bell inequalities if there is no collapse.
You don't even have to use the word quantum to understand Bell inequalities.
What?
You don't even have to understand the word quantum or even use the word quantum to understand Bell's inequalities and to understand why a statistical inequality can tell you about the nature is local or non-local. It has nothing to do with quantum mechanics. I mean, quantum mechanics has to obey it, and CSL has to obey it. And all theories that don't obey it will not account for nature in that regime. But I think it's wrong to say, and not I think, but it is wrong to say that we need something stronger than this no signal. I mean, then.
But okay, no signaling is very special. It's about signaling real signals, and the special relativity, we kind of the spirit. I do something here, and it doesn't. Nothing changed in Italy immediately. Currently, I'm in Tel Aviv. And if I have the superposition of a photon here and in Italy, and I look if it's here, I will remove the wave function in Italy or will make it bigger. So this is action at a distance. I cannot signal because the probability for both action is half. And Bell inequalities here are not relevant.
I think
this is
a
the
longer
point here.
discussion. Yeah,
So I don't want to go into this discussion because it goes beyond. I just want to the scope of the talk of today. I just make one comment that I think that what Lev, I might suppose, has in mind is a radically different worldview, which is the one that is linked to many worlds, where you wouldn't even formulate best theory in the way you usually formulate it. What this worldview is about, that's what I would question. But I can take it that in a many worlds worldview, let's say, best theory, I don't know if it doesn't hold, you cannot even have the hypothesis. You don't have space-time, the usual space-time. You don't have anything you usually grab to.
No. There is a space-time, but there's no Bell inequalities. But there are more people who want to ask questions to more to your talk. So
so thank you, Lev. So the next one was Michael. Nice to see you also.
Yeah, nice to see you, and thank you for a great talk, Matteo. It was very clear and crisp. And but I had, as a Dane, I mean, I had to comment a little bit about the Copenhagen interpretation in the beginning of your talk, because I mean, you're talking about this distinction between when is something microscopic and when is something macroscopic. To my way of viewing, let's say, the measuring problem, I will say that you can formulate it slightly differently, such that it's a matter of if it's possible to measure something or not. I mean, so you don't have to really you don't have to specify from the beginning. I mean, how does your observer look like and how does your system look like? I mean, the main thing is that could you make, I mean, the question if a collapse happens or not is a matter of, could you in principle make a measurement or not to determine between one and the other situation? And that's the whole, I mean, that's the whole background of, let's say, quantum Monte Carlo. I mean, so you, I mean, if you do quantum Monte Carlo, you don't think about how does your measuring device actually look like, but you're caring about if it's possible to measure something or not. I mean, so it's, I mean, it's a way of kind of, I would say, putting aside the problem of of discussing what is an observer or not. I mean, how big does it have to be? I mean, you kind of rephrase it in a way that's saying that in order to a collapse to happen, it's a matter of if it was possible for you in some way to measure if a collapse had happened. I mean, you don't have to tell about where do you put your detector or whatever. I mean, if an atom for instance, decay by spontaneous emission, the photon will come out in any direction, in all over 4 pi at least, with a certain probability. But you don't have to have a detector that covers the whole space in order to have a to have this effect going on in the dynamics of your quantum system. Actually, I mean, so it's just a matter of you could if you in principle could have detected where there was a photon coming out, that is enough that it collapses actually. So I'm just saying that, I mean, that that the need of an to define how the observer is not really so crucial actually in quantum mechanics. I mean, it's more a matter of would there be a possibility in principle to measure or not?
Okay, I will definitely not go against Weinberg's words myself, but I think I see your point. So the point is, if I understood correctly, is if you were able, or for example, not were able to, in this case, to detect the superposition, no, the console. Yes, this is also the case, but then one would also like to try to understand so in view, say in this Copenhagen interpretation view, eventually you want to have, say, if you take the von Neumann chain, no, and then you have this entanglement running over the scales, and then you have the superposition of the measurement apparatus as well. And then you say, okay, this is not the actual classical level, then the collapse happens at some other level. So for example, then you move up and you move up. Then I would say that you want to, at certain point, that this process breaks. in a way, no?
Yeah. No, it's not like you're really. I mean, you're not solving the measurement problem. It's as such. It's just like you don't have to worry too much about how your measuring device is looking like. I mean, but it's still you're still concerning with a measurement device that is outside your quantum mechanical world somehow. I mean,
yeah, exactly. You want something that is classic. That doesn't govern that.
Yeah.
Exactly. This is the also the say the prescription in a way, or the idea of these collapse models. No, should not be something that stay in the quantum realm, but should be something different. So.
Okay. Good. Thanks.
Thank you.
Thank you, Michael, who, by the way, will be a speaker soon in this series. So the next one is Jan.
Hi. Yeah, thanks for the talk as well. Very nice. So I would have two questions. The first is maybe if I understand something correctly, and then one building on this. So this lower right portion of this parameter plot of CSL, if I understand correctly, this is just, if those were the parameters, then the CSL would be useless to explain why we don't see macroscopic superpositions, right? And the left half? So the lower left?
No. This is the full gray.
Okay, but do you have maybe an intuition? Because I understand the right. Because I mean, we don't see superpositions on some big.
Yeah. I will explain this. Okay. So I can tell you how this gray line and the lower bound was drawn, and so this gives you already the idea, no? So the idea here is to take the small. So let's say now we are reading of the measurement apparatus. We ourselves are the measurement apparatus, no? So we are killing every middleman in the game. Essentially, how do I perform measurement is with my eyes. So my eyes determines which are the characteristic length and time scales of a collapse process, if there is a collapse process, no? And then essentially what you do is to take the smallest possible object and say, because that I can see with naked eye, and say in which time scale I'm able to see this object and it's possible or not superposition, no? So you think, okay, let's say I have this object, small object, it's placed in a really small superposition, and because I don't see such a superposition, it means that it has decayed in a time scale which is shorter than the one of my eye, of the one that is resolved by my eye. And essentially what comes out is that you play with the numbers. You came out with some sort of interferometric experiment, total interferometric experiment, that gives you this line here. But because this is a thought experiment, is a theoretical thing, you are not putting so it's essentially is one of these bounds that is just lowered here, but it is not an upper experimental bound, it's a theoretical lower bound. And this is the idea why you have this and why it has this V-shaped. Does this answer your question?
Okay, so there are, so the Gedanken experiment somehow works that there are really small objects for which
this is micrometers, some 10 of micrometer dimension object is a graphene disk, for example, and you really place it in a superposition of some. It's a total experiment, no?
Yeah.
But I don't see such.
Actually, my only question is why does it go down on the left from the dip? Just this point. I mean, I understand that it goes down as the object goes smaller.
Because the dimension of your system is around here. So you have say you start from here. So this is
this is the smallest thing you. Okay.
Yes, you can see. So this is the coherent action of CSL on your object, no?
Okay.
So if RC is smaller, then you have incoherent action, and so the effect is weaker. If RC is larger, then is not a focused action, and so again it's weaker.
Okay,
that's the reason.
That's the difference. Okay, then what I was wondering, so what if CSL is right, but the parameters are way, I don't know, the rate is way smaller And so it isn't actually able to explain why we don't perceive macroscopic superpositions. But to me, it seems it could be still useful. Or I mean, I'm asking whether you think it's still useful. I think it could be still useful to reduce like the worlds. So if it would be like a combination of many worlds and GRW, and to some extent we are in superpositions of observing two outcomes at once, but then there's a really slow rate of collapse or a really long range of collapse that just reduces this humongous amount of many of alternative worlds, but it's on a length scale, on a time scale, which is not sufficient to explain why we don't perceive the superposition. So you would have the many worlds argumentation that explains that, I mean, you're part of one branch, therefore you only
I
see one
see your
version.
point.
Yeah. I mean, would you
Who
say
knows?
this would still be a useful application of GRW?
Well, depends on what you mean. You mean as useful, no? But I mean, it's not a theory. It's not a construct that you can just kill with simple arguments. I don't think so. It could make sense that every time you make a decision, you double the universes, but after some time, this universe is also decay because of some GRW or something. So
Exactly.
This is the idea. I don't have an answer definitely on this one. Might be something to be developed on. I never thought about it.
Okay. Thanks.
You're welcome.
Okay, good. So Lev is protesting on the chat. I leave you to protest on that. So I think that we are running out of time. I would say it's already about 1 hour and a half. So if there are not further questions, we might call it for today.
Yeah, maybe if someone still thinks about a further question, I could quickly say we have Eddie Chen about probabilistic laws as I think next upcoming speaker. I think in the week beginning of March, and yeah, would be very happy to have at least some of you participating, or maybe telling your colleagues or other people, so we can have a nice discussion like today. Thanks, Matteo.
Thank you again also for the invitation, for giving me the space for talk.
But Angelo, you have the final word today, as
Yeah, the final words. No, well, I mean, it's thanks for you all that participated. Thank you, Matteo, for the talk. Thank you for the discussion, and thank you, Dirk and Paula, for a lot of organizational effort. And see you next time.
All right.
Have a nice afternoon and evening. Bye bye.
See you guys.
Thank you. Cheers.
Till soon. Bye bye.